Okay, so here's the problem. A small solid cylinder of radius r and mass m rolls down a smooth hill of height h from rest and gets onto a plank of mass m lying on the smooth horizontal plane at the base of the hill as shown in the figure. So here's a cylinder, here's the hill, here's the slope of the hill, and at the base there is the plank. Due to friction between the cylinder and the plank, the cylinder slows down and starts rolling without slipping on the plank. When the cylinder is rolling without slipping, the velocity of the plank is Vp, the velocity of the center of mass of the cylinder is Vc, and the angular velocity of the cylinder is omega. The coefficient of friction between the cylinder and the plank is mu, acceleration due to gravity is g, and the plank's height is negligible. We have to determine the velocity of the center of mass of the cylinder after it starts pure rolling, the velocity of the center of mass of the cylinder plank system when the cylinder is rolling over the plank, and the minimum length of the plank required for the cylinder to begin pure rolling over the plank. Okay, so in that initial descent down the slope of the hill, there is no friction and therefore there can be no rolling. So it's just an issue of the cylinder sliding down. Okay, so using conservation of energy for the initial descent, there is no friction, there is only translational motion, no rotational motion. So we have the potential energy mgh gets converted to the kinetic energy at the base of the hill. So that's half mv squared. From that we get v equals to root 2gh. That's equation 1. Now the cylinder has landed on the plank. Due to friction, now the plank will accelerate and the cylinder will both decelerate in terms of translational motion and it will start some rolling. Eventually the cylinder will roll without slipping on the plank. Now the frictional forces, that of the cylinder on the plank and the plank on the cylinder, are internal to the cylinder plank system, so we can still use conservation of energy. There will be half mv squared is the energy at the base of the hill just of the cylinder. That must be transferred to the translational kinetic energy of the center of mass of the cylinder, half mvc squared. But the cylinder is also rolling at that time, so rotational kinetic energy half I omega squared, plus the plank is also moving, so it has the kinetic energy half m vp squared. Now the moment of inertia of the cylinder is mr squared by 2. The angular velocity will depend on the relative speed between the cylinder and the plank, that is Vc minus Vp. That is the relative speed of the cylinder on the plank. That divided by r will give you the angular velocity. So we get half mvc squared plus half times mr squared by 2 times vc minus vp by r whole squared plus half mvp squared. Simplifying this, we get half mv squared equal to half mvc squared plus 1/4 m times vc minus vp whole squared plus half mvp squared. We multiply this equation by 4 and cancel the m term, which is common to all terms. We get 2v squared is equal to 2vc squared plus vc minus vp whole squared plus 2vp squared. That gives us 2v squared plus is equal to 2vc squared plus vc squared minus 2vc plus vp squared plus 2vp squared. And finally we get this 2v squared is equal to 3vc squared minus 2vcvp plus 3vp squared. That's our equation number 2. Now there are no external forces, therefore we can use conservation of momentum. So for the entire cylinder plank system, initially remember the cylinder is the only one that's moving, plank is not. Finally they're both moving and the center of mass of the cylinder plank system has a velocity of vcm. So we have the initial momentum mv, which is contributed only by the cylinder. That's equal to 2m, both cylinder and plank have a mass m, times vcm. From that we get vcm is equal to half v, and therefore we get vcm is equal to half of root 2gh. Now let's consider the cylinder and plank separately. We'll get momentum of the cylinder initially will be equal to the momentum of the cylinder plus the momentum of the plank. From that we get Vp is equal to V minus Vc. That's equation 3. Let's go back to equation 2 here. Equation 2, you can see that if I interchange Vc and Vp, I get the same equation, which means Vc and Vp, this equation 2 is symmetric with respect to Vc and Vp. But the cylinder is rolling on the plank, and therefore we must have Vc to be larger than Vp. So we substitute from equation 3 into equation 2 for Vp, and we get 2V squared is equal to 3Vc squared minus 2Vc times V minus Vc plus 3V minus Vc whole squared. Expanding and grouping terms, we get the quadratic equation 8Vc squared minus 8VcV plus V squared is equal to 0, and we can solve this now. So Vc is equal to 8V plus square root of 64V squared minus 32V squared divided by 16. We take the larger of the two, so plus sign instead of minus, because Vc is greater than Vp. And from that we get Vc is equal to 2 plus root 2 divided by 4 times V. Substituting for V from equation 1, root 2gh, we get Vc is 2 plus root 2 divided by 4 times root of 2gh. And then using the symmetry of the quadratic equation, we get Vp to be 2 minus root 2 divided by 4 times root 2gh. Now there's a frictional force. The frictional force is simply mu mg, because it's just the cylinder sliding along the plank. So the acceleration of the plank will be equal to the deceleration of the cylinder, and those both will be A equals to mu g. So the relative acceleration between the plank and the cylinder will be twice that. So 2 mu g. The initial relative speed between the plank and the cylinder is simply the speed of the cylinder at the base of the hill. So that's root of 2gh. And the final relative speed between the plank and the cylinder is simply Vc minus Vp. We found both of them on the previous slide. Subtracting and simplifying, we get root of gh. Now we use the equation of motion, v squared equal to u squared plus 2as, and we get Vc minus Vp whole squared is equal to v squared minus 2a rel times s. That gives us gh is equal to 2gh minus 4 mu gs, which gives us s is equal to 4 by h by 4 mu. And this is the minimum distance the cylinder should move relative to the plank before it starts pure rolling.